Okay, back at it. Get full screen here. Okay, we're going to do just a few more problems. So it's part 2 of your homework Monday night, and hopefully you're just following. There we go. Get that hair down. All right, let's see what's coming up. So we're going to do a kind of an entry-level related rates problem, a little bit of Arcsine work. We're going to take a derivative and then integrate forwards and backwards so that you can start to get some experience recognizing, as that's all it's all about, recognizing what you're looking at as to how you go about solving or performing that mechanics. And last thing we'll do is an optimization problem. Of the 3 problems, I think that's probably the most difficult one we'll cover tonight, but got to dive in. So let's do it. And we'll start with that entry-level related rates. The Arcsine is a little more straightforward, so we can intellectually take a little break in between the 2 more difficult problems. So let's say you're heating a metal plate. Pretty typical problem here. Now you're heating it up, and evidently the metal is expanding. It's circular, plate's circular. So the radius length is increasing at 0.04 centimeters per second. And when the radius is 50 centimeters, at what rate is the area of that plate changing? Okay, so I'll state that again because I didn't write it out succinctly. Metal plate, heating it up. Circular in nature, right? Plate circular. The radius is increasing at 0.04 centimeters per second. And when the radius is 50 centimeters, at what rate is the area of that plate changing? All right, so to get a feel for that, I think we'll get an eraser. That's how we'll get a feel for it. We'll just erase the problem off the board. No. I guess I was going to show you this, but I'll take that back. So let's go back to day 1. You got the area of a rectangle, well, a square in this case, x times x. At what rate is it changing? That's the bumpity process, right? And that should look real familiar. That's dy, little change in area, x and an x, right? A dx and a dx. We got ourselves a differential statement, dy equals 2x dx. And it becomes a derivative when we compare the change in y to the change in x. Then we have a rate of change, which is a comparison, right? Miles per hour. You're comparing things, right? And it's based on the geometry of that, which is basically doubling the length of the side of the square, right? Both of them. Right, so what do we have? We got area of a circle, something that's circular, pi r squared. So how does the area change? 2 pi r dr. 2 pi r dr. Okay, and I think that was in a previous video. Can't remember which one, but it was recently that we really dove into that. Maybe it was how we were looking at this whole topic to begin with, I think. Done so many test grading and progress reports and videos, I can't remember what I did when. But related rates are comparisons. dr dt. So we want to divide both sides by dt. Oh, now I have how does the area change with respect to time? How does this change with respect to time? Still equal. Did the same thing to both sides, right? So now the question is, what did those things mean? Oh, the radius length is increasing at 0.04 centimeters per second. Well, that's what dr dt is. So that's 0.04 centimeters per second. When the what? When the radius, we'll multiply 2 pi out here. When the radius is 50 centimeters. Well, there's only one unknown now. It's dA dt, which is what we were trying to find. Okay, so we have 2 pi times 50. Why don't I say 100 pi right now? 100 pi centimeters. 100 pi centimeters times 0.04 centimeters per second. Well, that's nice. Centimeters times centimeters is centimeters squared, right, per second. Well, that's nice because we are talking about how the area is changing. So it should have some square units to it. And then all of this is a little math. And so it looks like dividing by 2 decimal places times 4 gets me, well, let's write this as 4 over 100 to show that more clearly. 4 over 100, right? So we're multiplying that times that. It looks like the hundreds cancel. And we got 4 pi centimeters squared per second as an answer. I think that, yeah, I think you can see all of that. Okay, so that gets us kind of started in this topic. And we'll delve into it more as we go along. All right, next problem. Pretty straightforward problem. Don't know what we will have covered in class because I'm doing this before Monday here, Sunday here. And I think I live here now. Beveridge, this little office room here. Did I ever leave here? I think I'm trapped. I think I'm quarantined. All right, here we go. All right, so let's say y equals arcsine, pure mechanics here, arcsine of x cubed. Can you find y prime? That's for the memorization, right? But as a reminder, y equals arcsine of f of x. The derivative, y prime is equal to, can we see up there? Yes. The derivative of what's inside, which is f prime of x divided by the square root of 1 minus whatever is inside gets squared. All right, so what is our answer here? I'm going to write it way down below. Right here. The derivative of x cubed is 3x squared. The square root of 1 minus x cubed gets squared, so that's x to the 6th. I'm going to leave it as x cubed squared. Okay. Why did I leave it like that? Because we got to be able to integrate these things. We got to be able to go backwards. We got to be able to integrate this dx to get back to y. Why did I erase it? Y equals arcsine of x cubed. Well, first thing is recognition. What's your u? X cubed. Right? Pause the video and try these yourself, obviously, right? So what's du? Oh, du over 3x squared equals dx. Okay, so that means I've got 3x squared, I've got the square root of 1 minus u squared, and I've got du over 3x squared. Oh, well, that sure looks like these cancel. I'll take them right out of there. Well, I won't take them out. 3x squared goes in and 3x squared. You better write the number 1. Well, that sure looks like the arcsine of u plus c. And your last step is to do what? Replace u with x cubed, and you're right back there. Okay? It's going to take a little practice for you to be able to see that. So we'll give you plenty of practice. All right, the hardest one of the 3. Optimization problem here. Probably going to throw you, but we'll keep at it. We will keep at it. You stop the video and you try it on your own. But I don't know how far you'll get because I think this stuff takes experience and practice. Well, let's start with a function square root of x. Let's see. Let's get a little look-see at that. Square root of x. And I would like to find the shortest distance. Where on the curve would I be? You know, so that I've got the shortest distance between 3, 0 and a place on that curve. All right, so you think about that a minute, and we'll go after it. I don't know if this is going to morph into a calculator problem or not. If it does, then obviously got to use one. If it doesn't, you don't. I got no clue. Let's find out. I think this is a distance. Oh, so what is this coordinate here? How do I represent it? Because I guess I got to have the distance formula here. Distance is equal to the change in x squared plus the change in y squared square root, right? I mean, that's what you do. You got X, you got Y, you got a distance, right? You can do what? You do X squared, you do Y squared equals D squared. So if we just want D, it's the square root of the sum. Okay, so the issue really here is defining that point, but we don't know what it is. We don't know what that point is, but I do know there's an X value here. I do know it has an X value, and it's got a Y. But that's a two variable equation. I wish there was some way that I could think of getting it to a one variable equation, because then I'd have some hope of solving it. One equation, one unknown, that's solvable. One equation, two unknowns, big problem. Two equations, two unknowns, hey, that's solvable. Two equations, three unknowns, that's a problem. And the problem gets rectified if you can rename one of those unknowns in terms of the other variable. I think we can. I think that's the square root of X. Ah, I guess I can do the distance formula now. So the distance equals the square root of 1x minus the other is the change, top minus bottom. I got to square that change, and top minus bottom. Got to square that change. And I know square roots, smallest of square root can be a 0. I studied that last term. Yeah, so, and square roots only get bigger. So I guess the smallest distance is going to be when whatever is inside is smallest. So I guess we just have to look at our distance, sort of, is represented by x squared minus 6x plus 9 plus x. If I minimize that, I'm going to find that x value. I don't know if it's going to be a nice x value or not. Let's find out. So x, that's going to be minus 5x plus 9. Oh, it's not so much fun. It's not a lot of fun here. So we'll set it to 0, and then we'll knock it out of the park with completing the square. But at this, well, wait a minute, I haven't taken the derivative yet. Excuse me. So I want to minimize that, so therefore I'm going to go d prime sort of. Oh, 2x minus 5. Well, that's not so bad. So x equals 2.5. All right, and then you would do what? You would take the square root of it, and that would be the location. So that we now know the coordinate. So we didn't need a calculator. 2.5 or what? 2.5 halves. And the square root of 5 halves is the coordinate that minimizes that distance on the square root function to 3, 0. All right, so hopefully I didn't make any mistakes, but doing a lot of work here. I find that fatigue sets in a little bit for me now. I get careless. I tried not to be careless on the midterm. I still made a couple of math errors. Ah, terrible. Awful. Anyway, I guess to be human is to make mistakes. So that should have concluded, hopefully, a foray into these topics this afternoon. We just did that. And here's a little more practice. And some of you I hope to see at Math Help. And that'll be 8 to 10. I don't think we need to go 7 to 8 at this stage. So it'll just be 8 to 10. And practice some of the things we're looking at. First test will be next a week from this coming Thursday and Friday. I'm going to break the test up in 2 parts. 25 questions Thursday, 25 questions Friday, because I'd like to proctor those exams next week and see how folks are doing. All right, so you want to stay in touch with, you really need to look at the answer key to the last test, to look at what you got wrong. Those of you who are doing that, making some incredible progress from test 4 to test 5, probably should have stressed that more, probably should have done a written key sooner. But certainly there'll be a written key for Thursday and Friday, and a written key going forward. Videos can be made of topics that cause you problems. Happy to make videos on a request format. going forward, but I'll make videos on these problems the whole week. All right, so that's where we're at. Looking forward to having everybody back in the classroom and doing worksheets at the board. I think we're going to find that very useful experience. I hope so. And hope everybody can make some gains in this course going forward. See you soon.